All right, triple integrals. I know what you were thinking. You were thinking to yourself, you know what? What I really need is I need something that's actually more tedious to do than double integrals. Double integrals were just not enough calculation for me. I mean, really, just not enough. You know, just needed to do more calculation, needed to like do more plug and chug, needed more opportunities to make random mistakes as I'm trying to do integration. And so I come to you with triple integrals. Here you are, triple integrals, enjoy. In all seriousness, although that is the experience of doing triple integrals, at the very least, we do want to at least have the experience of doing triple integrals. We do want to know how they're done. And theoretically, you want to actually be able to do triple integrals or to think about triple integrals because it's a gateway to actually doing integration in higher dimensions. All right. Now, integration in higher dimensions, in all honesty, we're going to do that with a computer. And the fact is double integration, double integration, triple integration, and all it gets done with computers. But you want to be able to like kind of think about the process of doing multiple integration. Okay. And so we're going to look at triple integration. We're going to think about this from the perspective of, all right, here we did it with two, right? That was over a surface. Okay, or we had a surface and that was over a rectangular region or a more general region or a spherical, a polar region. And now what we're going to do is we're going to say, okay, what if now I have a function of three variables? Okay, and so in a physics perspective, you've got your three variables, you've got your x, your y, your z, and then you're going to have a time variable. That time variable is kind of like if you imagine that you've got this volume that's moving through time. All right, and we want to know what's happening with that volume at a particular time, right? Or we might want to, know something about that object, how it kind of comes up. If you kind of remember those level surfaces, that's basically like the idea of like taking a snapshot of a volume as it moves through time. And so, if you want to think about it from a physics perspective, that's kind of the physics aspect. More practically, when we talk about a triple or quadruple or quintuple integral, I've got a function of many variables. I've got a function of many variables, and since I have a function of many variables, and I may want to know something about like its integral, right? Okay, I want to do some kind of accumulation. I might want to know an average function. I might want to know the probability of something occurring based upon a lot of these different integrals, or I might have a differential equation of multiple integrals, right? A higher order, not a higher order one, but I might want to find a differential equation for something that actually has a lot of different integrals, and so I need to do multiple integration for that, okay? And so consequently, you kind of need to at least understand what the process is for working with triple integrals. We're going to do this one here, which is going to be rectangular. We're going to work in rectangular, and then we're going to do another one where we're going to work in spherical and also cylindrical, which is more of a physics engineering based one. All right, so let's start in on triple integrals. All right, so basic theory for the triple integrals, I'm actually not going to get into the whole summation notation. Don't really need to do that. We did that with double integrals. Going to keep away from that. What we're going to just talk about is we're just going to talk about a volume, right? So let's say, for example, I've got f of x, y, z. So it is a function of three variables. And what I'm going to do, if you remember when we did it in two variables, right? F of x, y, for example, we integrated over something on the xy plane. Now what we're going to be doing is we're actually going to be integrating over a volume. And that's where things get kind of like a little weird from a physics standpoint. But at least we can talk about the volume that we're going to integrate over. So let's imagine that we got some kind of prism. It's a rectangular prism of some sort or another, okay? And it looks like this, okay? And if we think about it, okay, let's say, for example, this is our delta x, this here is delta y, and this is delta z, okay? So we got delta x, delta y, and delta z. The change in x, the change in y, and the change in z, right? So these are little regions, right? These are parts of our volume. If you imagine that we're going to break up our volume into these parts, each one of them being a box with the delta x, the delta y, the delta z. And if you remember, as we're working through integration, what ends up happening is that when we take that limit as t goes to infinity, okay, delta z, right, is going to go to dz, delta x is going to go to dx, and delta y is going to go to dy. right? It's good. Those ones are going to transform as we take that limit towards infinity. So we're going to end up with that dx, that dy, that dz. Now, you do an integral in higher dimensions. Basically, you're going to get the same exact thing. It's just that we're not going to be able to actually draw a picture of it. All right? So we got these. These are our little pieces. These are the little pieces. And then what we're going to do, essentially, okay, is you're going to imagine, all right, I've got a value called f of x, y, z sitting right there somewhere in the box, okay? And so essentially this is going to be whatever the value is for the fourth dimension. So you've got your delta x, your delta y, your delta z, and then you have, call it f of xi, f of yi, f of zi star, okay? And that'll be a value for your function. So what we end up with is we end up with like f of xi star, right? F of yi star, excuse me, not f of xi star, f of yi star, f of zi star, right? Okay. And then we got our delta, let's do it, we're going to do, say, delta x, delta y, delta z, if we want to do it in that order. And you kind of imagine that's going to be, this is going to be what we call a hypervolume for the cube. A hypervolume because it's four-dimensional. 1 dimension, 2 dimensions, 3 dimensions, 4 dimensions, right? So it's four-dimensional, and so we call that a hypervolume, right? We're going to accumulate those all up. We're going to add them all up, right? Take them like really, really, really small pieces, right? For some region, okay? So we imagine this is our region here. Let me see if I can make a kind of a different looking region. There's 1 dimension. There's our 2 dimensions. This is just terrible. But you can kind of like, hey, let's imagine that's a 3-dimensional region, right? We've got our little regions inside of those, okay? And then we're just going to accumulate up all those little hypervolumes, okay? And when we do, what we're going to get is we're going to get a triple integral, okay? We get this triple integral for whatever this region is. And we're going to call this region, we'll call it E, okay? And so E is just made up of lots of these little boxes, right? E is going to be bounded by either a set of functions or a set of variables, and we'll talk about that in a little bit, or excuse me, a set of bounds. And so we'll end up with this triple integral, and it'll basically just be f of x, y, z, and then dx, dy, dz. We want to put it in that order, and there you go. Now, what you'll see that this is actually also going to be written as the triple integral over the region E, and it'll be f of x, y, z, whatever that function is, and then dv, where dv that's the general volume. And we'll utilize that dv there because sometimes when we're like working in cylindrical or we're working inside of spherical, dv is going to be actually found slightly differently. It's not just going to be dx, dy, dz. All right, so now let's look at like a prism region. So what we got here is we've got something that's going to end up being a prism or some kind of box. All right, so what we've got here is, what you'll see is B, and B actually indicates for us that we've got a prism region. All right, E is going to be a general region, B is going to be a prism region. Okay, so the volume of a prism is is x times y times z. All right, and that's why we're going to get our dx, dy, dz. Okay, so that dv is going to end up equaling, in our case, we'll do it dx, dy, dz. Okay, now here's our box, here's our prism, and so I'm going to draw it in 3 dimensions, just to give us a real clear sense of what's going on here. And so we're going to have on the x-axis, we're going to go from -2 to 1, okay? All right, so we're going to go from -2 to 1 on the x-axis, maybe a little bit closer. Then on the y-axis, we'll go from 0 to 3, 2, 3. And then on the z-axis, we're going to go from 1 to 5. 1, 2, 3, 4, 5. Okay, let's see how we do here. All right, so we're going to go 0, 1. So there's our first corner for the box. This corner right here, that's going to be 1, 1, 0, 5. Okay, we'll go up again second corner for the box, right, is going to be the corner 1, 0, or excuse me, 101, 101, and then 105 for the second corner. Okay, we'll go out next corner, right? Okay, up to -2. So this is going to be -2, 0, 5. It's the next corner. Okay, so there we go. All right, and then well, actually, we can take this out. A little strange there, but that's going to be the corner 1, 3, 1. Okay, and then we can go out and we'll go up to. Let's see if we can make this. Freehand is always easier. There we go. There's the next one, right? Okay, next one. Right, and if you need to, you can go in and you can actually draw out each one of the corners. Okay. Is it a perfect box? No, it's not a perfect box, but hey, there you go. There's our volume there, okay? We actually also have another point right here if you want to kind of get into that. It's kind of hiding behind the scenes, okay? And then there's that last line on the box, and there's our volume, okay? There's our volume, and it gives us, we get our bounds for the integration. All right, and there's the bounds for the integration. And so what we're going to do is we're going to set this up. We're going to have 1, 2, 3 integrals. I'm going to do x first, so I'm going to go from 1 to -2. And then I'm going to go from 0 to 3 for y. And then z is going to go from 1 to 5. Okay, so here's your x, here's your y, here's your z. Then we have the function x squared y z. And if you remember from double integration, we just need to we need to go the opposite direction. So this is going to be dx, dy, dz. Okay? We're going to go inward, out. Okay? So this is zyx, this will go xyz. Or if you want to think from the inside out, xyz. All right? Now we're going to get into this. We've got Fubini's actually for a generalized region will allow us to switch the order in any way that we want to, as long as we have our functions written correctly. And we'll talk about that in a little bit. But in this case, we could switch the order in any way that we want, as long as we're integrating in the right order. Okay, so you want to make sure that you are actually integrating in the right order. Otherwise, you know, you're going to end up having the wrong bounds for each variable. So let's do this now, and the process is exactly the same as it is for double integration. Okay, so what I'm going to do first, I've got my double integral here, and I'm actually just going to consider x squared yz dx. So I'm going to take that integral from 1 to 2 of x squared yz dx. Okay, and I've got my other integrals here, 1, 0, 3, okay, and 1, 5. And just for demonstration purposes, let's just see, we're going to hold y and z to be constants. So basically that's going to become yz, and then this will be x cubed over 3, and we're going to evaluate from 1 to 2. Okay? So what that gives me then is this is going to end up being yz times 8 over 3 minus 1 over 3, okay, because it's going to be 2 cubed minus 2 cubed over 3 minus 1 cubed over 3, so that ends up being 7/3. So that's 7/3 yz. Okay? So now I've got my next two bounds of integration. So I've got 7/3, the integral from 1 to 5, 0 to 3, and then yz, and now I've just got a double integral in dy dz. Okay? So now I'll integrate with respect to y, because that's the next one. All right? And so that's going to end up being y squared over 2, and this will be z times the integral, or excuse me, it's going to be integral from 1 to 5, and this is going to be z times y squared over 2, evaluated from 0 to 3. Okay, and then we'll have our 7/3 there as well. And so this ends up equaling 7/3 times the integral from 1 to 5 of z times, and this is going to be 8/2, or 4, minus 0, which just equals 4. So I can take this and I can multiply it by z again. Okay? So this is the integral. Now it's going to be 28 over 3, 28 over 3 times the integral from 1 to 5 of z dz. It's got a dz on it. It's got a dz on it. And so this is now 28 over 3 and times z squared over 2, evaluated from 1 to 5. So this ends up being 28 over 3 times 25 over 2 minus 1/2, which is 24 over 2, or 12. So it's 28 over 3 times 12 over 1, which equals 28 times 4, and that's 112. 112. There you go. And so 112 is our answer. Notice the process is identical to the work that we did with double integrals. It's just now that we got to do it 3 times. We've got to treat our variables. Any variable that I'm not integrating with respect to gets treated as a constant, and that's one of the reasons why I just pull it out, because it's a constant. Like, it operates as a constant, so I can just pull it out of whatever it is that I'm integrating, okay, and then just deal with it later. Now, theoretically, integration over a general region is a little bit more tricky. Okay, so like what we're going to have is we're going to have a general region. We're going to call it E. E is going to be my general region. And if you remember, we're going to have D. D is a disk. And in general, for without a loss of generality is what we say, we're going to imagine that this is on the XY plane. So it's on the XY plane. We've got this disk D. Okay. And so what we're going to do is we're going to say, okay, I want to imagine that I've got 2 functions. I've got, say, for example, z equals, and we're going to use u1 of xy, okay? And I've got z equals u2 of xy, okay? And on the z-axis, we're going to imagine that u2 of xy is the outer function. And we've got u1 of xy is going to be like our inner function. The one that's closest, this is closest to the xy plane. And this one here is the farthest from the xy plane. And it is a very similar idea to what we were doing with double integrals. Where what we had was there was a lot of different ways that you could go in, and you could there were 2 different basic ways that we could work with the region. We could either write our function with respect to x, or we could write our function with respect to y. It was totally up to us. And all we really needed to do is we needed to make sure that we had our outer function and we had our inner function. We had both of those, and we actually defined what they were. So that's going to be kind of similar here in this case too. I mean, there's going to be a lot of different ways we could do this. There's actually, if we think about it, there's going to be 3 different ways that we can think about this in general. That is that we could have a function of z, or we could have a function z, which is a function of x and y. We could have a function y, which is a function of x and z. Or we could have a function x, which is a function of y and z, right? And we'll look at some examples of that. But for our purposes right now, we're just going to consider a z, okay? And let's imagine I've got this region, okay? And on top, right, here's my surface. That's my top surface. It's we're going to call this z equals u2. This is going to be u2 xy. And then I have a bottom surface. Let's say, for example, that this thing here, it looks like this. There's my bottom surface, okay? And what I've got here is I've got a, kind of like a solid that looks like this. And so this is z, this was z equals u1 of xy. There's the bottom one, okay? And what we want to imagine is that this is going to be over some kind of region, okay? It's going to be a projection. We're going to project onto D. So D here is going to end up being in our XY plane. Okay? So here's the Z. We've got D. D is, is going to be flattened out. Okay? And we're going to project both Z equals U1XY and Z equals U2XY onto D. All right? So when we did this as a double integral, you just had the one surface, and the one surface got brought down onto D. Okay? In this case, you've got 2 surfaces. You've got a top surface and a bottom surface. Okay, so you've got a top volume and a bottom volume over this region D. And what we're going to need to do is we're going to kind of, basically we're going to subtract the volumes. Essentially, is what's going to happen. We subtract these 2 volumes in order to get our the overall hypervolume, basically to get the overall hypervolume. Okay, so this gives me my volume. Actually, scratch that. Not my hypervolume. It's going to be my volume. And then we're going to have generalized values for f of xyz. okay, that will be inside of this volume, right? So we've got to construct our volume, and that's what we're doing here, right? So this is the construction of the volume. And then we're going to evaluate, okay? We're going to evaluate f of xyz, like we're going to imagine that we've got an f of xyz in here, okay, that we evaluate inside of that volume, all right? And then we accumulate all those volumes up together, and what do we get? We end up getting the value of the triple integral, okay? Kind of tough to conceptualize. Basically what you're going to do is you're going to want to think to yourself, you want to extrapolate up from 2 dimensions. So in 2 dimensions, we had a disk D, or we had some kind of region D, and we had a surface. And that surface, we found the volume of that surface. What we're going to be doing here now is we're going to take, we've got 2 surfaces, the top surface and the bottom surface, and essentially what we're going to do is we're going to subtract the volume, those 2 volumes, in order to get our new volume, okay? Our dV, right? Essentially, it's going to be our dV. And then f of xyz, we're going to multiply f of xyz times that volume, okay? And that'll give us the value of the triple integral. All right, so now we've got like a triple integral over a general region, and what we're going to be doing, we're just going to be thinking about this in terms of z. You could think about it in terms of y, you could think about it in terms of x, and in higher order integration, you could be in terms of any variable that we want to. You're going to notice here, I've got E as my general region. X, Y, Z, those are values within E, within that volume. X, Y is the region D that we are going to be essentially evaluating U1 of XY over and U2 of XY over. Okay, so Z is a function of X and Y. Okay, and XY is this region D. What you'll see when we do this in a practical sense, when we actually go in and do it, that Y is going to be a function of X, right? And that Z is going to be a function of X and Y. So what's going to happen here from a practical perspective is we're going to start out by integrating with respect to Z. We'll get rid of the Z variable, right, by evaluating the function for X and Y. We'll be left with functions of X and Y. We're going to take those functions of X and Y, then integrate with respect to Y, and then integrate with respect to X, okay? And that's just going to be our first example. You can literally do this in any order that you want to, okay, as long as you are constructing your functions of Z, your functions of X, your functions of Y correctly, okay, and are placing them in a correct order. Now, when we look at our integration here, okay, we've got D is said to be the projection of E. So from a theoretical perspective, that helps us to kind of imagine what's going on, right? And we've got our triple integral, f of x, y, z dv is going to be equal to the double integral over the region D. Okay, so now we're going to say, okay, so I'm going to pull out one of those. I'm going to pull out a dimension. Okay, so now this is an area because it's a double integral. Okay, and then I've got this single integral with respect to dz. So I got the dz. Okay, and that's going to be my third, my third integral there. Okay, and that's going to basically allow me to like accumulate all of my volumes. And then this here is the integration of this volume over this region, okay? And then, of course, we've got dA, which is left over for my double integral. Let's not worry too much about this, okay? As you're working and as you're thinking, right, you want to say, okay, so what's happening as I take the triple integral? And I'm going to point this out as I go along. As I take the triple integral, I'm basically pulling off, right? I'm pulling off a dimension, right? One of the dimensions is now being evaluated. Okay, so now I've added a dimension. I'm like, oh, I've gone from points or like one dimension. I'm now up to 2 dimensions. I'm now in an area. I go from an area to a volume, and then I go from a volume suddenly to a hypervolume. All right, and that's kind of the idea. I'm like adding in a dimension each time as I integrate. I'm accumulating dimensions. All right, so now let's take a look at this, and we're going to evaluate this triple integral, and that's f of xyz equals 5x minus 3y. And our region that we're going to be looking at is given by the planes x equals 0, y equals 0, z equals 0, and the line x plus y plus z equals 1. So what we're going to do now, I'm going to actually kind of draw the picture so I can see what it looks like. Okay? And so what we've got is x plus y plus z equals 1. So I've got the point, right? Okay, if this is 1, here's 1, here's 1. This point here, 0, 0, 1. that's on the plane. Okay. Then I also have 1, 0, 0, also on the plane. And then I have 0, 1, 0, also on the plane. And those end up being my bounds for this thing that kind of looks like a, kind of like a tetrahedron or a triangular prism, okay, or a pyramid. And so now I'm looking at this, I'm going to go, oh, okay, cool. So one, I need a function, right? So essentially I only have just the single function of z, okay? So, and that single function of z is this thing here. So that's z equals 1 minus x minus y, okay? And that's going to be over a region D, and this is our region D, okay? So our region D is this thing down here. That's the projection onto the xy plane. So it's that region right in there. And what we know, or what we can see here, is that this region is going to be bounded by, okay, basically the line, it's going to be y equals 0, okay, up to y equals whatever this thing is right here, okay, whatever that value is. And so notice that z equals 0 for the region D. And since z equals 0, what that means is that we get 0 equals 1 minus x minus y. All right. And so consequently, if I add over y, I end up getting y equals 1 minus x. And so that ends up also being, ends up being the value for the region D. That actually ends up being the other bounds for the region D. It goes from y equals 0 down here, all the way up through y equals 1 minus x over here, okay? And then x is going to go from 0 to 1, okay? So x is going to go from 0 to 1, right? And we can kind of see that from the graph there too. Those are the bounds for x. So now let's think about what's going on here, all right? So first, all right, if I think about it just in single dimensions, the one that I have the value, the values of x for, that's x goes from 0 to 1, all right? And so those are not actually functions of anything else. So that's going to be the outer bounds of my integral. So it's going to go from 0 to 1, okay? Notice these are constants. And then I'm going to add on a dimension, all right? So next up, we're going to go with y, all right? And y is going to go from 0 to 1 minus x. And then I'm going to add in my z by adding in the y now, okay? And so this is going to go from 0 to 1 minus x minus y. And then it'll finally be just our function, 5x minus 3y. And we notice this is z, that's dz, dy, dx. Okay, so that setup is really probably it's the hardest part, really, because the rest of it kind of looks a lot like what we did with double integrals. So you start out, right, we've got a function for z, right, okay, x plus y plus z equals 1, that's going to be the three-dimensional surface, right, okay, that's that kind of is going to help us to be the top plane here, okay, and then we're going to say, okay, so I can rewrite that in terms of z to being z equals 1 minus x minus y. And I'm also going to note that that's going to go from 0 up to there, whatever that value is. And that's this plane right in here, right? That's that plane. Then I need to go in and I need to figure out the bounds for d. Now, d could be type 1 or type 2. In this case, we did it as type 1, all right? And all we did there was say, okay, well, if z equals 0, okay, if z equals 0, what's the function for y? And we plugged it back into this function right here. And we get 0 equals 1 minus x minus y. Boom, there you go. There it is. And then finally, x, we just had to figure out the bounds for x. What's my minimum value? What's my maximum value and my minimum value? And then those became the last set of boundaries for our triple integral. All right, let's go in and let's actually evaluate this. So now, I am going to first go in and I'm going to evaluate with respect to z. Notice that there are no z's there. 5x minus 3y then is just going to be constant. So what we get is we get 5x minus 3y, okay, times 1 minus x minus y minus 0, okay? Or actually, let's just write this. This is a z evaluated from 0 to 1 minus x minus y. And then we'll have a dy, we'll have a dx. And here's our other integrals. 0 to 1 minus x, 0 to 1. We'll evaluate z from 1 minus x minus 0, y minus 0. So that's just going to be 1 minus x minus y. So this is going to then be the integral from 0 to 1 minus x times 5x minus 3y times 1 minus x minus y dy dx. And then we've got the integral from 0 to 1. I'm actually going to go in and multiply these two together. So this is going to end up equaling the integral from 0 to 1, the integral from 0 to 1 minus x. And this will be 5x minus 5x squared minus 5xy minus 3y plus 3xy plus 3y squared dy dx. This ends up equaling the integral from 0 to 1, 0 to 1 minus x. And this is, we'll just write this as 3y squared minus 5x squared plus 5x minus 3y minus 2xy dy dx. Now what we need to do is we need to integrate with respect to y. So this is going to give me 0 to 1. We're going to get y cubed minus 5x squared y plus 5xy minus 3xy. Oops. Somehow that 3xy came in there. I don't know where that came from. Oh, that's plus 3y. Plus 3y plus 3y squared over 2 minus 2xy squared over 2, or basically just xy squared. Well, let's do x squared, 2xy squared over 2. Okay, so we're just integrating with respect to y, treating x as if it's a constant. So it's dx. And then we're going to evaluate that, by the way. We'll evaluate from 0 to 1 minus x. So I'm going to take a break here. I'm going to go in and I'm going to actually evaluate this for you so you don't have to just watch me do a bunch of algebra. All right, hopefully now that you've done that, what we get is we get something that's going to end up integrating, simplifying down to the integral from 0 to 1. And it'll be 1/2 x minus 1 squared times 6x minus 1 dx. And now what we've got to do is we've got to just integrate this whole thing, okay? And when we do that, what we end up with is we end up with 1/12. All right? So what you can see here, I mean, so you're going to have to do some algebra. I've got to say that the algebra is it could be a little bit challenging, especially as we work more with polynomials. I think sometimes the trig is going to be a bit easier. But the process is exactly the same way as what we were working with before. Okay? It's basically, once we've set up our integral, you're going to treat each variable that you're not integrating with respect to as a constant. And then that's going to allow you to do your triple integration. All right, so now let's actually use the triple integral to find the volume of a sphere. And let's say the sphere is x squared plus y squared plus z squared equals 9. And what we're going to do is we're going to imagine the sphere in 3 dimensions. Okay, so we've got the sphere in 3 dimensions. We know that the radius of the sphere is going to be 3. So we've got basically in the first quartile, it's going to look, it's going to look something like this, right? So it's going to be the first quartile, and then we're going to kind of imagine that we're going to go all the way around. Okay, not the greatest sphere in the entire world, but there we go. And there's our sphere, okay? Going all the way down here, 2z equals 3. All right, this goes out to y equals 3. Okay, we're also going to go back out here to y equals negative 3. We'll have z equals 3. Or not z equals 3, but x equals 3 is this point, by the way. That's that value right there. And we'll go out here to negative 3 on the x-axis as well. And actually, if I rewrite this to be more concrete or more accurate, this is the point 0, 3, 0. This is the point, not z equals 3, but rather 0, 0, 3. This is 3, 0, 0. Out here is negative 3, 0, 0. Up here is, or excuse me, this is negative 3. This is 0, 0, 3. And this is 0, negative 3, 0. Okay, so we've got the sphere. And if you remember when we wanted to find area, all right, what we would do is we'd take the double integral, and then our function would be f of xy equals 1. Now we're looking to find volume. So if we just want to find the volume of a figure, what we need to do is we'll just find the region. We'll actually kind of like dictate what the region's going to be. And we're going to use the function f of xyz equals 1 to find volume using a triple integral. Now what I'm going to do here is I'm actually just going to go in and I'm going to set up the integral so that we can kind of see what imagine what the integral looks like versus going in here and actually evaluating the whole thing, because this figure is much better evaluated using spherical coordinates or cylindrical coordinates, right? Because well, you see it's just going to be a little bit of a mess. So we're going to get first the bounds for z. So we're going to get z squared, right, is going to equal 9 minus x squared minus y squared. Right? That's just taking this function, transforming it to z. So z is going to equal plus or minus the square root of 9 minus x squared minus y squared. Okay? So what that means is that we're going to have our u1, if you remember our u1 of xy, or u2 of xy is going to be the top value, and that's going to be the positive square root of 9 minus x squared minus y squared. And the bottom is going to be u1 of xy, and that's going to be the negative square root of 9 minus x squared minus y squared. All right, so that actually helps us to define our volume in terms of x and y, and so that's going to be the first set of bounds for our integral. The next thing is to figure out what d is. Now d is this figure right here. It's that circle. Okay, so it's that circle right there, and that's our region d, right? And so basically we know what that is, or we're going to know what that is. That's going to be when z equals 0. All right, so that's going to be x squared plus y squared equals 9 for our region D. And so hence y squared is going to equal 9 minus x squared. And so y is going to equal plus or minus the square root of 9 minus x squared. Okay? And so consequently, we can let our, call it w. So y is going to equal w1 of x, which equals the square root of 9 minus x squared, the positive. And then we'll also have y equals w2x, which is going to equal the negative. And that's going to be the bottom end of 9 minus x squared. And so now that gives me my y. So we started out, we found our z. We set z equal to 0 in order to kind of like allow for the function to project down onto the surface. Okay. And that then we, go solve for x in this case, or excuse me, solve for y. And now we're going to actually just find x, and you can see that x is going to go from negative 3 into 3. Okay? So x has to be greater than or equal to negative 3 and less than or equal to 3. So when we set up our integral, we're going to have this triple integral. Okay? Well, let's first do the interior integral. The interior integral is going to go from negative square root of 9 minus x squared minus y squared, okay, to the square root of 9 minus x squared minus y squared. And then we're going to integrate for the y's. That's going to be from negative square root of 9 minus x squared to the square root of 9 minus x squared. And then we'll integrate again, going from negative 3 into 3. Okay? And then our function is just 1, and then it'll be dz, dy, dx. Okay? Now, if you look at this, you're going to say to yourself, oh my goodness, this would be so much easier if I were working spherical. Yeah, that's going to like actually motivate us to start working in spherical, and that's exactly what we're going to do very soon. I'm not going to go through and evaluate this because it's a mess, right? Or it's kind of difficult, and we'll get lots of practice doing that. But what I do want to actually notice, or have you notice, is that what we could do is we could, since we're symmetric, and we're symmetric with respect to the x-axis, the y-axis, and the z-axis. So what we could do is we could actually just take 8 times, and just do this first octant, right? The positive octant. So we go from 0 to 3, and then the integral from 0 to the square root of 9 minus x squared, and the integral from 0 to the square root of 9 minus x squared minus y squared, and then 1 dz dy dx, and that would also be the same integral for us, right? Because we've got eight regions that look like that, right? Got top, bottom, top, bottom, top, bottom. Okay, right? Yes, that's it. There are 8 of them. I just had to take a quick thought through there. I had to make sure that I was doing that correctly. All right. So there we go. So this is actually another option. Notice, right, the setup, and that's actually what I want to get at. That's why I gave this example. The setup starts out with, okay, I've got a picture, or basically an idea of what this is going to look like. I've got an upper and lower bound for z based upon x and y. Then I set z equal to 0 because I'm going to project down onto the xy axis, so z equals 0, or xy plane, because z equals 0. Okay, I find y, right, and then I establish my bounds for x, right? And that happens to be if we want to do it in this order. So now what we're going to do is we're going to talk about changing the bounds of integration. And we can actually do that similar to the way that we did it with double integrals. And oftentimes we're going to do this because it actually just makes the work a lot easier, or because our functions happen to be in those terms. All right. So like, let's say, for example, we want to evaluate over the region E the square root of x squared plus z squared dv, where E is the region bounded by y equals x squared plus z squared, and the plane y equals 4. So we look at this figure here, okay? So that's the figure right here, and the plane y equals 4 actually is like, it's this plane right in here. There's like a plane. You can't see it, but basically what it does is it sets up the bounds. It sets up your bounds for integration, okay? So essentially what we've got here is we've got like that kind of endpoint there of the value 4, okay? And so what I notice here is I've actually got my bounds already set up for y in terms of x and z. So the question is like, why would I go out and rewrite this in terms of z, and then write it again in terms of x, and then write it again, or excuse me, in terms of y, and then write it in terms of x, when that just doesn't seem to make a lot of sense? I mean, it just doesn't, right? It looks like the best thing to do is to start out by integrating with respect to y, right? Because we've got these values for y, then integrate probably with respect to z, and then finally go back and integrate with respect to x. All right, so let's think through what exactly we're going to be doing here, okay? So we're going to allow, this is going to be our volume, and our volume is going to be defined by y equals x squared plus z squared, and that's going to be the bottom end, okay? So notice, right, that's the value that's closest to this xz plane, okay? So that's going to be the lower end of our first set of bounds for our integral, and the top end is going to be the y equals 4, right? Because that's going to be the outer end. So like you imagine, okay, I've got the plane x equals z, okay, and then I've got on the other end I've got y equals 0, and then on the other end I have y equals 4, right? And so my inner curve is y equals x squared plus z squared, and my outer curve is y equals 4, okay, right? And that's just kind of like, imagine, right, what's your inner, right? One closest to the origin, the outer is one farthest from the origin. And then the next thing that I need to do is I need to imagine what D is. Now remember, D is a projection, but D doesn't have to necessarily just be a projection onto the xy plane. In this case, what makes more sense is to project down onto the xz plane, and what we get is we get this circle here, right? Okay. In fact, we get this thing here, that circle right there. Okay, that's going to be that projection onto the plane. So in this case, y is going to end up equaling 4. Okay, so that disk D is going to end up being 4 equals x squared plus z squared. So we get z squared is going to equal 4 minus x squared. So z is going to equal plus or minus the square root of 4 minus x squared. Or we get the bottom end, right? We got our u1 being z equals the square root of 4 minus x squared, and our u2 being z equals negative square root of 4 minus x squared. Okay? Right? And so, more than basically, it's just, what we're doing is we're projecting down here onto the plane right? If we set y equal to 0, we end up with just the origin. The origin is going to be the only value. It doesn't make any sense. So our region D is going to be that projection of the entire figure down onto the xz plane, all right? And that's why I replaced y equals 4 into the function, okay, to give me that circle. And then finally, we need the values for x, okay? And so the values for x onto the xy for that circle in the region D now are going to go from -2 to 2, okay? Because those are the values for the projection onto the xz plane for that circle, right? So x is going to be greater than or equal to -2 and less than or equal to 2. So what I'll do now is I'll say, okay, cool. So I'm going to have 3 integrals. The outside one, I'll have that be my x1 because that's going to be my actual value is -2 to 2. Then I'm going to have z negative square root of 4 minus x squared to the square root of 4 minus x squared. And then my y, again, remember our outer is going to be y equals 4 and our inner is x squared plus z squared. So this is going to be x squared plus z squared. And this is going to be 4. And then we're going to have our square root of x squared plus z squared. Square root of x squared plus z squared. dy now, because remember this is a function of y, dy, dz, dx. So in this case, we changed our order of integration in order to allow ourselves to be able to do an easier integration and an easier setup, right? Okay, something that actually is more effective for us. And then what you'll do is you'll go in, evaluate with respect to y first, then evaluate with respect to z, and finally evaluate with respect to x. Okay? All right, so what we're going to do now is we're going to actually evaluate the integral. And so I'm going to first integrate with respect to y. Notice that there are no y's in here. Okay? So this is going to be the integral -2 to 2, the integral -4, square root of 4 minus x squared, comma 4 minus x squared. Okay? And then we'll get, this is going to be y times the square root of x squared plus z squared, evaluated from x squared plus z squared to 4. Okay? And that's dy, dz, or excuse me, dz, dx. All right? So we'll plug that in. This is going to be 4 minus x squared minus z squared. So this is going to be the integral from -2 to 2, the integral negative square root of 4 minus x squared to the square root of 4 minus x squared. And this is going to be 4 minus x squared minus z squared times, and this is the square root of x squared plus z squared, dz dx. Now what I'm going to do is I'm actually going to say, okay, well, you know what? I can change this into polar. Okay, I can actually transform this into polar. And what I'm going to do is I'm going to actually let x equal r cosine theta, and I'm actually going to have z equal r sine theta. All right, so I know that we've always had that y equals r sine theta, and that's true. However, it doesn't really actually matter from the perspective of working inside a polar, because now what we've gone is we've gone from a 3-dimensional figure down to a 2-dimensional figure. So you can just choose whichever one you want to be, you know, the horizontal, and whichever one you want to be the vertical. So we could actually make this substitution, okay? And in addition to that, remember, because we're doing a double integral, that dz dx is going to end up equaling r dr d theta, okay? And we're going to do that for a very good reason, because it's going to make the integration a lot simpler for us. So this is going to be the integral now. Well, first, let's figure out what this is. 4 minus x squared minus z squared, and x squared, the square root of x squared plus z squared. Notice that r, right, remember r is going to end up equaling the square root of x squared plus z squared, right? Just substituting in, like we're basically y equals z in this case. And then, so that means that 4 minus x squared minus z squared, okay, 4 minus x squared minus z squared is just going to equal 4 minus r squared. Okay? Now we look at this, negative the square root of 4 minus x squared, okay? And all the way up to 4 minus x squared. If you kind of think about this, this is a circle. In fact, we don't need to just sit here and think about this. Remember that we actually had a circle here, okay? And this is a circle of radius 2. That's x squared plus y squared equal, or x squared plus z squared equals 4. So the region here, okay, is going to go from r equals 0 to r equals 2. So my bounds for r, are r equals 0 to r equals 2. Okay? And then we need theta, and if you think about it, theta is going to go from 0 to 2 pi. Okay? So bounds for theta. So now we've rewritten our region. Our region D, okay, was the circle with radius 4. How do you rewrite that region D in terms of r theta? R theta is then going to be r greater than or equal to 0, less than or equal to 2, and theta greater than or equal to 0, less than or equal to 2 pi. So now our setup looks like this. It's going to go from 0 to 2 pi times the integral from 0 to 2. Okay, here's r, here's theta. Okay, this is going to be 4 minus r squared times r dr d theta. Okay, and that is a supremely more simple integral to actually solve, right? Okay, wow, that's easier to work with. So we're gonna kind of see this in a couple of different places. This one actually turns out it's kind of easy to work with. It's like cylindrical. You'll notice, right, what we needed to do, we needed to integrate with respect to y first. We actually needed to remove one of those variables. And then to notice that our region D was a circle. And circles are just so much easier to work with in polar. All right, so at that point, noticing that our region was a circle, we actually switched to polar, okay, utilizing x equals r cosine theta, z equals r sine theta, and these values for r, okay? And by sketching out our region, we could actually see what the bounds were for r and what the bounds were for theta, okay? Then you could just go in and solve this, and it's actually a lot easier. And our answer here is going to end up being 128 pi over 15. Okay, and that's going to end up being your answer when you get done. So now let's take a look at a single application here of triple integrals, and that is finding the average value of a function of 3 variables. So what we're going to do, you're going to notice that this is going to be very similar to the work that we did in 2 dimensions. It's just now that we've added another dimension, so instead of, say, for example, 1 over the area, it's now going to be 1 over the volume. All right, and actually, if you went to more variables, it would be like 1 over the hypervolume, right? And the process is pretty much identical. You're just adding on an integral each time. So it gets more and more complicated as we, increase the number of variables inside of any kind of system, and that's just the nature of adding variables. It does get more complex, but from a certain thought perspective, it's pretty much the same thing over and over and over again. We're just gonna, like I said, add an additional dimension each and every time. So the average value of our function is going to be 1 over the volume of E, and that's the region that we are finding the volume for, times the triple integral over E of our function times dv. Okay, so basically the triple integral of the function over the region E divided by the volume of E. Right? And if you notice that that's the same thing that we did with double integrals, and it's the same thing that you do with single integrals as well. Okay? And so like that process could be right there. Notice as well that the volume of E is going to be defined by the triple integral of 1 dv. Okay? So let's take a look at an example of this. So let's take a look at this example. Let's find the average value of the function f of xyz equals xyz over the cube with sides of length 4 units in the first octant, with 1 vertex at the origin and edges parallel to the coordinate axis. So let's draw this out. Kind of think to yourself, okay, what does this look like? And so it's a cube, and we've got 1, 2, 3, 4. The edges are going to be 4 units, 1, 2, 3, 4. 2, 3, 4. Okay, so there's that. We go out to here. And so it turns out, okay, what we've got here is we've got a simple rectangular region. All right, so this region is our box B. It's going to equal the set x, y, z. All right, such that x is greater than or equal to 0, less than or equal to 4. Y is greater than or equal to 0, less than or equal to 4. And z is greater than or equal to 0, less than or equal to 4. Okay, there's our box. And so consequently, my volume v of e, okay, is going to equal the integral, and we'll do dz dy dx for sake of ease, 0 to 4, 0 to 4 again, 0 to 4, and this is then 1 dz dy dx. Okay? Now, if you got a different region, you got a different way to find the volume, but we're just doing an example here. So first thing we want to do is find the volume. Okay, there's our first, find our volume. So integrate with respect to z first. So this gives me the integral from 0 to 4, 0 to 4. This is going to be z evaluated from 0 to 4, dy dx. So this is the integral from 0 to 4. And this is now going to be 4. So this is going to be 4 times the integral from 0 to 4, 0 to 4 dy dx. So that'll be equal 4 times the integral from 0 to 4. Then this is just going to give me a y. And that'll be evaluated from 0 to 4 dx. So that's now 4. 4 minus 0 is 4. So it's now 16 times the integral from 0 to 4 dx, which just equals 16 times x evaluated from 0 to 4, which equals 64. And that's the volume. Now that's the volume of E. Okay? Now what we need to do is we're going to take 1 over 64 and we're going to integrate over B, right? Our box B. So we're going to get the integral from 0 to 4, 0 to 4, 0 to 4, and now our function x, y, z, dz, dy, dx. You could, of course, do it in any order you want. It's actually not going to change the value of this integral at all, given the fact that our bounds are all the same. So what we're going to do now, we got 1 over 64, got the integral from 0 to 4, integral from 0 to 4, okay? And then this is going to be then z squared over 2, evaluated from, actually it's going to be xy times z squared over 2, evaluated from 0 to 4, dy dx. Notice 4 squared is 16, divided by 2 is 8. So this is going to be, this thing up here is going to end up being 16 over 2 minus 0 over 2, which equals 8. So this is going to be 8 over 64. We'll pull out the 8. And now 0 to 4, 0 to 4, xy, dy dx. We will integrate with respect to y now. So this is now 8 over 64 times the integral from 0 to 4. And then this is going to be x, because x is constant. This will be y squared over 2, evaluated from 0 to 4, and dx. Notice that y squared over 2, it's got the same bound, so it's going to be 8 again. So we now are going to take our constant 8 out again. So this is going to equal 64 over 64. Well, we know what that is. That's 1. Okay? Times the integral from 0 to 4 of x dx. So this is then just going to equal, and that's 1. 1 times x squared over 2, evaluated from 0 to 4. And that then is just going to equal 8. And so 8 is the average value of this function over that rectangular region. This average value function actually ends up being really, really handy in a lot of applications. It also is something that comes up quite a lot inside of mathematics. So kind of understanding that process where what we do is we imagine whatever the region that we're integrating over, whether or not it's an area, a volume, a line, or, you know, a hypervolume, or like a really, like what we, a bigger area, region, like a manifold or something. And then we integrate, we figure out what the multiple integral is over, for that function over that region. And that always gives us our average value, okay? So, set up the region, okay? Figure out what that region looks like. That's first and foremost, okay? That's the hardest part of the work that we're going to be doing. And then, utilize the process of, like, basically treating each variable that you are not integrating with respect to as a constant, and then integrating with respect to whatever variable you're looking at, okay? Very systematic. Got to be honest with you, it's kind of time consuming too, okay? So, you know, be patient. It's going to take some practice, all right? Luckily, I didn't assign too many of these. Okay, so that completes our work with triple integrals over general regions. We're going to be looking at triple integrals for cylindrical and polar in just a little bit. That's going to make a lot of this a lot easier too, especially for certain kinds of regions.